Jinyi's research has just been exceptional over these many years, looking at PET image reconstruction, optimization of that imaging for lesion detection, et cetera. And his group has really been made many seminal contributions, everything from improving resolution with including detector design into the system matrix, as well as looking in dynamic reconstruction with their kernel-based methods, and then more recently looking at deep learning effects now to do that. So Jinyi's talk today will be something very near and dear to my heart during direct estimation of kinetic parameters from PET. Take it away, Jinyi.
Thank you, Rich, for that kind introduction. So let me share my screen here. So I hope you're seeing the presentation.
Looks good. Thank you.
Okay. Yeah. So good morning, good afternoon, or good evening, so everyone. Welcome to the webinar. So today it's my pleasure to give a talk on the direct estimation of kinetic parameter in PET reconstruction. And really, I thank the invitation from the OpenKMI modeling initiative. So just try to follow the steps from the two previous seminars. So the two previous ones mostly focus on the application. So today we're going to take a deep dive into the algorithm, and I'm going to give an introduction and some motivation about why we do direct estimation, and then briefly review the history and focus on a few methods from the simplest one to the more computational efficient ones. And then we're going to discuss some unique issues in the direct estimation and conclude this webinar. First, let me just give a quick overview about dynamic PET. So after administration of radioactive tracer, the tracer are being delivered by the blood, and at any tissue site, there's this exchange and the metabolism of the tracer. So this kinetic process gives the time change of the activity distribution at every voxel. And PET scanner detect those 2511 keV photons generated by positron annihilation. And from there, those events are either sorted into a dynamic sonograms or kept in the list mode data. And those data can be reconstructed based on image model according to the Poisson distribution of the data, and to generate a series of images that depict the tracer activity distribution over time in the human body. And then for every voxel, we can generate this time activity curve, and which then fit into this mathematical model of the tracer metabolism. So then we can estimate those rate constants. So for example, K1, K2, K3, K4, and then generate these parametric images. Essentially, it's a parameter value at every voxel. This is the traditional way of doing dynamic imaging to provide estimation of the parametric images. And we call this indirect estimation because it consists of two steps, two separate steps, I would say. One is the image reconstruction, the second one is the connected fitting. Our approach we're going to talk about today is the direct estimation of the parametric images from the sonogram data. Okay? And whether we're going to form some intermediate image or not, it's not important, but the goal is really to work from the raw data directly and try to get an estimate of parametric images. The first question you may ask, so why we want to do this, since the indirect estimation is so simple to implement. The problem is, as shown on this slides, the indirect estimated parametric images can be very noisy. This is an example taken from this reference by Angeles in 2014. It shows the estimated parametric images of K1, K2, K3, and Ki and the blood volume. So you can see some of those parameter images are really noisy, right? So then the question is, how can we reduce noise? Obviously, one option is to increase count. So because the PET data is follows the Poisson statistics, the higher the count, the better the SNR. At least that should be. So there are several avenues we can increase count So increase injected dose, increase the scan time, or increase the photon detection efficiency. All of them have their limitations. I will describe in more detail in the following slides. So let's look at the first one, try to increase injected dose. Obviously, the concern is the radiation risk, whether it's there or significant or not, that's a different debate. But the guideline is we should use as low as reasonably achievable dose. And also, there's also another issue related to the PET data acquisition. So the data we acquire in PET image reconstruction, and what we want are those true coincidence events, where the 2, 5, 11 keV photon come from the same positron decay, and we call that true coincidence. And there are cases the PET detector may actually detect two photons, each from separate positron decay, and those are two completely independent. And those two single photons can occur at the same time, so the PET system may consider there's an annihilation occur between this line, but there's nothing occur. So this is called a random event. And because of the two detections are independent, so the random coincidence rate increase quadratically with respect to the activity level, as shown on this graph. So this is a random curve as a function of activity level. And this one is a true coincidence rate as an activity level. As you can see, when we increase injected dose, the random fraction actually increases. So the signal to noise ratio may not increase. And also the PET system has a limit capability of counting events. So in fact, when we have more activity inside the field of view, the noise equivalent count rate may actually decrease as a function of injected dose. So just simply try to increase injected activity doesn't necessarily translate into higher SNR. And some typical range of the injection has shown here. So for FDG, we may be able to increase double the dose maybe, but for rubidium and C11, there's not much room for the increase in activity. The second one, we can increase the scan duration. This works very well for static scan. And as many people have seen, when people do denoising, they use a longer scan as the label for training network. But it doesn't work that well for dynamic scan because dynamic scan is already very long. So it's already 1 or 2 hours. And due to the radioactive decay, there's a diminishing return by increasing the scan time. So some, for example, for C11, it's 20 minutes half-life. We already scan 1 to 2 hours, then there's not much count remain even if we scan any longer. Okay. So the next option is to build a better scanner that has a higher photon detection efficiency. So this would be the example Explorer scanner that has been built. It's 2 meters long, so provide very high photon detection efficiency. But the problem is it's very expensive. Not everyone can afford such a long axial field of view scanner. So this brings us to the second option. Okay, can we have a better way to be more efficient utilization of every photon that we detected? So this leads us to the direct estimation of kinetic parameters from raw data. It has several benefits, and there's no extra radiation, no additional scan time, and also there's no additional hardware cost. Okay. So as I mentioned, direct estimation can reduce noise. And let me just give you some examples before we get into details about how we do that. So this is a brain scan using a C11 AFM acquired on HRT scanner with a 20 millicurie injection and 2-hour scan. The same data being reconstructed using the direct reconstruction methods on the left column and the indirect methods on the right column. So the K1 is the first row, VT is second row. For both of those parametric images, you can appreciate the lower noise generated by the direct reconstruction methods as compared to the indirect approach result. And here's another result taken from another reference by Angeles. And this is the FDG brain scan. So as compared to the indirect result shown in the middle row, that's what I already shown in the previous slides. So the direct reconstruction on the first row really substantially reduce the noise, and you can now actually see the brain structure, okay, in the images. Even though we could reduce noise by post-filtering the indirect reconstructed image, but you can see it's lost the resolution, so we don't have a lot of details in the brain structure. The same thing applied to whole body PET imaging. So, so this is the result taken from the paper, Panelist, and they show the direct Patlak reconstruction can reduce the noise and improve the image quality over the indirect reconstruction, either for the standard Patlak, so S Patlak, or the generalized Patlak model. So in both cases, the direct reconstruction produced higher image quality. Okay, so now I hope I convince you, so the direct reconstruction is useful. And now let's look at how we do the reconstruction. So here's a few papers that propose the direct reconstruction. So the first two by Snyder and Carson Long, both either in 1984, 1985. So those two papers really laid the groundwork for performing direct estimation of parametric images. Okay, and however, neither of those algorithms were implemented at the time due to the limitation of the computing power. So about 10 years later, so in 1997, so Matthew et al. So proposed to perform direct estimation of parametric images for linear kinetic models. In particular, they show the result of direct estimation and compare with the feedback projection reconstruction. And 2005, ChemSet showed the direct reconstruction of nonlinear compartment model kinetic parameters and show the benefit of direct reconstruction. And those papers really generate a lot of interest, renewed interest on direct estimation of kinetic parameters. And since then, so there are many people have developed direct reconstruction for both the linear parametric images, different graphic analysis model, Patlak, Logan plot, and a generalized linear model, etc., as well as nonlinear parametric images, including one tissue model, and two tissue model, and reference tissue model. I should know the direct estimation also being developed or being applied to other imaging modalities as well. So there's a lot of early work on SPEC reconstruction. Some of them are driven by the requirement of the slow rotation of SPEC, and where the whole sequence has to be reconstructed at the same time. Or some later work is really try to use the direct reconstruction to reduce noise. And it also has application in the dynamic MR to estimate the kinetic parameter as well. For people who are interested to probe into further, there's at least a few review papers here. Okay, so now let's get into the mathematics of direct reconstruction and how we do it. The basic idea is fairly simple as long as we have a kinetic model. And here we're going to focus on this compartment model. So we have a blood concentration we denote by CP. And there are some intermediates. So the free tracer distribution we denote by C1. So this could be the free FDG inside the cell or unbounded tracer. And then there's another component denotes the metabolized tracer or bounded tracer. Okay, so there's an exchange rate between those compartments. And this, the rate of change of C1 and C2 can be described by those two differential equations. And from there, we can solve those two differential equations and get the expression of the C1 and C2 over time. And the tissue concentration is essentially the combination of C1 and C2 and plus some blood fraction. And this is what we're going to measure in PET scanner. And we call that X. So it's essentially the CT integration over the scan duration of each frame. And we put that X into the imaging model. So Y equals to P times X. And where P is the projection matrix, R is the background events. And each individual measurement follows by the detector beam follows a Poisson distribution. And based on this noise model, then we can formulate an objective function based on the likelihood function and some regularization function. So we have an objective function. We basically then maximize the objective function with respect to the kinetic parameter to get an estimate of the parametric images. So relatively simple idea. The difficulty here has arisen in several ways. The first one is this compartment model. It's nonlinear in the way that those K1, K2, K3, K4 are related to the image activity nonlinearly. Okay. And one solution is we can actually use some linear model to do approximation, as well I will show next. And the second difficulty is the high dimension. So we actually now basically have millions of image voxels, so J, and then we have a number of kinetic parameters, so we actually multiply them together. So it's a substantially increased number of unknowns in the estimation. And also the most difficult one is the spatial temporal coupling. Okay, that's causes a lot of problem, and we have developed methods to address that. So let's go to the first one. So to solve the nonlinearity problem, we can use some linear model to simplify the estimation. One example is the Patlak plot, and this is widely used for tracer contain one irreversible compartment. So it can contain many reversible compartments as long as there's one irreversible compartment. This model can be applied. Essentially, after some time, all the reversible components reach equilibrium, then the tissue concentration over the plasma concentration can be written into this linear form. Okay, it basically depicted by this graph here. So I have the red is the blood input function Cp, the green is the tissue activity curve C of T. So if I plot Ct over Cp versus the integral of Cp divided by Cp, then I got this linear relationship. This has been shown by Rich in the first webinar already. So essentially, we can fit the slope at a later time, so 15 minutes after 15 minutes injection for FDG, roughly. And to get this Patlak slope that is proportional to the glucose metabolic rate, it's a useful parameter for many applications. Okay. Because this model is linear, then we can actually just include this basis function. Okay, this linear basis function matrix A essentially has two columns. One column is the blood concentration Cp at all the different time points, and then the second one is the integral of the blood concentration at the different time points, and actually multiply those with the system projection matrix. And then this become our imaging model. So if we just consider this as a single matrix, this just looks like the same imaging model for static PET reconstruction. So then we can just formulate the likelihood function at the same Poisson distribution, and then perform this penalized maximum likelihood estimation. Okay, using any existing PET reconstruction algorithm, as long as we treat those A chronic product with P as a single projection matrix. Okay, in particular, if we don't have any regularization term, we can apply the standard MLEM algorithm and reach this falling update equation. It looks like just like the standard MLEM algorithm with multiplication between A and P together, right? The computation is fairly simple, very easy to implement. But people have found the convergence of this algorithm is extremely slow. Okay, and the reason is there's a very high correlation between the temporal basis function and in the Patlak plot, and actually in most linear models. Okay, and this approach does not applicable to nonlinear compartment. For the nonlinear compartment model, one ad hoc approach is to just combine the image reconstruction and kinetic fitting together into this iterative loop. So the algorithm just iterates between image reconstruction and kinetic parameter estimation over multiple iterations. However, this does not use the full noise information in the kinetic parameter estimation, so it has a similar issue as the indirect estimation, but it's improved the image quality, obviously. And another issue is it doesn't have any guarantee of convergence because those two steps are independent of each other. So our solution to address this problem is try to use this optimization transfer approach to derive some surrogate function to decouple this spatial temporal correlation as well as this the voxel and voxel-wise correlation. So the basic idea is to replace this original objective function defined in the sinogram domain as given by this phi function by some surrogate function that defined in the image domain that satisfy two conditions as I given here. One is they have matched value at the current estimate, so they touch over there. The second one is the surrogate function will lie below. Okay. Then if we maximize the surrogate function, we get to the new point, and it's guaranteed this new point will have a higher objective function than the original point. Okay, and therefore this guarantees the monotonic increase of the objective function. And also by the two conditions, we can guarantee this iterative procedure going to converge to the true maximum point of the original objective function. So over time, we have developed two type of algorithms using this optimization transfer, depending on what surrogate function we use. The first one we call class 1 is using a quadratic surrogate function. And essentially, this function is defined in the image space and is actually a separable quadratic function. So defined on each voxel and the summation over individual voxels. So and M is the time frame, so J is a voxel. Okay, so for each voxel, essentially is a weighted least square formula. And to construct this surrogate function, we need to compute. There's two parameters. One is the xj, m superscript n plus 1, and that is obtained by image update. This is just like one step in an iterative reconstruction. Essentially, is using the current estimate of the image plus the gradient divided by some curvature. So the gradient is exactly the same gradient of the objective function, and the curvature needs some calculation to make sure this surrogate function satisfies the two conditions that I mentioned in the previous slides. So some details will be given on the next slides. And it's the same for this, it's a weighting factor. Then the next step, we just need to minimize this function for each voxel, so that's just a kinetic parameter fitting step. Okay, so we can use any existing algorithm to do that. The advantage of this approach as compared to the iterative kinetic fitting approach is the weighting factor here is automatically determined by the surrogate function, so it guarantees the convergence. So just some details on the derivation of this separable quadratic surrogate function. It follows the procedure given by Fassler and Logan in 1998. Essentially, we write the likelihood function. So the I is the detector bin. So the sonogram bin number, M is the frame number, so different frames. And for each bin, we have a Poisson log likelihood function. And because this log likelihood function has a bounded curvature when the background events R is non-zero, then we can have a quadratic surrogate function for each individual log likelihood function. And this curvature eta here can be designed so that it has an optimum curvature that guarantees those two conditions. And then the next step is to use the convex property of this quadratic function here so that we can decouple the correlation between the different voxels. And so because essentially using this, rewrite the pxi using this linear combination with a defined pi. This is just this is by design. There's multiple choices. Essentially, the summation of pi will equals to 1, so it's a weighted average of multiple components here. So then, using the convex property, we can get a new separable surrogate function for each voxel. So there is a implicit summation over I over here, and then summation over J over here. So on this side, we sum over all the measurement bins. On this side, we actually sum over all the image voxels. And then for each voxel, as I mentioned previously, it's essentially this Z superscript n. That's just the new image update can be computed by taking the current update plus the gradient divided by the curvature W, and that W in the previous slides can be computed from this curvature eta, and then multiply by the projection matrix and divide by this weighting factor and sum over all the bins. Okay. So that's some details on the algorithm itself. So once we implement that, okay. So we did some simulation to demonstrate the performance of this algorithm. So we simulate a brain FDG uptake. And on the left column, that's the reconstructed image, individually reconstructed image, noisy. The top row is an indirect reconstruction, and bottom row is a direct reconstruction. And then we also compute the mean and the standard deviation images by running multiple noisy realizations. So the middle column is a mean image. It looks very similar. That's by design, so that it matches the resolution. And then the standard deviations, you can see the difference. And we can generate a plot profile. So here again, so just demonstrate the resolution, the mean image, they look very similar. So it has the same resolution, but the noise in the direct reconstruction is almost 2 times lower than the indirect case. And this reduction in noise is equivalent at least 3 times increase in count. So we just use the algorithm to get equivalent increase in count without any additional cost, patient discomfort. And this can also be applied to patient data. So this is a cancer patient data, and you can appreciate the direct reconstruction has better contrast in the KI image, right? As well as the K3 image to depict the location of that lesion as compared to the indirect reconstructed result. Okay, and there's also a second class of the algorithm. So here we, instead of using the quadratic surrogate function, we use the EM-based surrogate function. So the formula of this is given here again. So it's a separable in terms of voxel, but the form of the expression is given by the x hat times log of the expectation and then minus its expectations in terms of the Poisson log likelihood function. Okay, to construct this surrogate function, we just need to compute one parameter, that is x hat, that can be computed exactly using the EM update equation for the image activity. So just take the current image activity and multiply by this ratio of the back projection. And then the second step is to maximize this log likelihood function for every pixel to perform the Poisson likelihood fitting to find the parameter. This method is particularly useful for linear model because in the linear model, the M step can be solved by an EM type update as well. Essentially, because it's linear, then we treat the A as the projection matrix, then that's just, we get this EM update equation in the image domain for every pixel. Okay? And because it's A is very small, so it just contains the number of frames times 2. So this iteration can be run very fast. Okay, we're going to run multiple iterations here without increasing any computational cost. And after all the sub iterations, we're going to update the final parameter data, and then let's go to the back to the S step. As compared to the original EM methods, essentially, if you set NL equals to 1, this go back to the original EM methods. And this method has a guaranteed monotonic convergence, as we described earlier, because it follows optimization transfer principle. And it can achieve faster convergence than the original EM just by running multiple iterations here without increasing any computational costs. And this can also be further accelerated using the momentum methods. Okay? There's a little, basically rewrite the update equation as a gradient descent algorithm. And then we can apply this Nastrel's momentum methods to the class 1 surrogate function. So that's a separable quadratic surrogate function, and which has ellipsis constant. Right? It cannot be directly applied to the nested EM, at least in theory, because the EM update is not related to the ellipsis constant. Just to demonstrate the difference between those different accelerations, we apply those linear algorithm to this patient data. So FDG's brain scan on a PET-MR scanner with the MR-guided attenuation and motion correction, and we get a blood input function from the reconstructed image from those blood vessels. Those are segmented from the MR image and then extract the blood input function curve. So here we shows the 4 reconstruction algorithms. And what we plot is the MSE, so the mean square error, between the reconstructed image at every iteration with respect to a reference image that we obtain by running the nested EM with 20 sub-iterations and 5,000 iterations. So this is 500. So we actually run this so 10 times more to get a reference image, and then we compare all the others with respect to that reference. The reason we use the nested EM is to avoid give any bias to the momentum methods. Okay, so there's 4 curves, and the green one is we call the nested EM with sub iteration 1, and that's what we have said this is equivalent to the original EM by treating the product of A with P as a single matrix. So the convergence is really slow, as you can tell from this curve. When we have used 20 sub iterations, you can see the acceleration of convergence. So if we just match the MSE at this point, for the nested EM, that only requires 40 iterations to reach 500 iterations of the original MOM. Okay? And then the momentum is even faster. So this is the momentum methods with 20 sub iteration again. So if we match the MSE at nested EM with 20 sub iteration and 500 iteration over here, then we draw a curve, draw a line that's equivalent to 60 iterations of the SPS with momentum. Okay. This is on the Patlak slope image, and this is on the intercept image. Both of them show the same trend. We can also compare the images. This is the Patlak slope image. The slope image actually converges faster, so you don't see much difference between them. Okay, so let me just explain. So the first image is the 500 iteration as the EM sub 20 sub iterations. This is what we use as a reference. Essentially, that's corresponding to this point over here. And all the other images are 60 iterations. Okay, so the original EM 60 iterations. So the main structure you already see, but if you focus on the scalp regions, so you see this convergence hasn't get there yet. Okay, nested EM is getting better, but it's still different from the 500 iteration. Okay, with a momentum either using 1 sub iteration or 20 sub iterations, especially with 20 sub iterations and 60 iteration of the momentum, then we actually converge to the same image as the 500 nested EM algorithm. This difference is more pronounced in the intercept image because this image converges slower than the Patlak slope image. And here you can see with, again, the first one is the reference, 500 iteration, nested EM 20 sub iteration, which shows very flat intercept image in the gray and white matter. Now, if we look at the original EM with equivalent to 1 sub iteration, okay, so that's convergence. It's very slow, so you see this artifact that's generated by the slope image, okay? And with the 20 sub iteration as the EM, it's getting better, but still you see some residual artifact, okay? And with the momentum, this is get very flat, so uniform looks pretty much the same as 500 iteration of nested EM. Yep. Okay. So that's for the direct reconstruction. Okay. So another way to reduce noise, as we all know, from the image reconstruction field is to include some regularization. Right? This has been done by including a penalty function or a prior function. The traditional prior would be a pairwise or patchwise smoothness penalty using a quadratic function, as in the Chemistec 2005 paper. I'm using a sparsity-based, such as TV, in Yu et al. Paper, wavelet. And we can also use some anatomical information to get the regularization. Okay, for example, like the Bauscher type of prior, that's actually used in the previous example I just showed, using in the form of joint entropy. So here today, I want to just focus on a different type of regularization we call the representation-based representation. So here we want to regularize the image, reconstruct the image by a representation function. And two examples would be, one is the kernel representation, where the image is represented by a kernel matrix multiplied by a coefficient vector. And this is a linear model, so allow us to use very simple reconstruction algorithms, such as the nested EM. And the second one is a deep neural network-based representation, where the image is represented by an output of a deep neural network. And the advantage up here is the network has a greater capacity to learn the high-quality images. So I just want to explain those two, so one by one. So the first one is for the kernel-based reconstruction. So this is the traditional representation of the three-dimensional image volume. So there's 3 axes. What we're going to do is we're going to add additional attributes, so axes, so such as this co-register CT image, co-register MR image, or co-register high count pad images. I will show how we get those. Okay. Once we have those attributes, we put them together in as a attribute vector, and then based on the kernel learning principle, essentially we can represent an image in a high dimensional feature space that is a transform of those attributes. And then this representation can be simplified just into this kernel formula, where the kernel matrix is just the inner product of the transformed features, and then this alpha is the coefficient. And in our application, we just use the radial Gaussian kernel. So the kernel matrix computation is fairly straightforward once we determine what would be those attribute vectors, and just put into this Gaussian function. The advantage of using this kernel representation is we can combine this kernel representation directly with the image model of PAD, and so that we still have a linear model in this imaging system. And therefore, this can be solved using the standard maximum likelihood estimation. And just a special case when kernel matrix equals to identity, this just revert back to the conventional methods. Okay? And what we use is actually we just use the standard MLEM for the reconstruction because it's easy to implement. And here we don't need to do the nested approach between the kernel matrix and the projection matrix, okay? Because there's less correlation in the kernel metrics. Okay. So to generate this kernel metrics, we need those attribute vectors. So one way to get those attribute vector for dynamic pad is to reframe this 1 hour scan, so 360 seconds scan, into 3 longer frames. So this is 10 minutes, that's 20 minutes, that's 30 minutes. So then we got those low noise images. And then for each voxel, we're going to pick a patch, and those 3 patches will form the attribute vector. And that's allow us to compute this kernel matrix. And then using that kernel matrix, we can represent the Patlak parameters. So the slope will be the k times alpha, and the Patlak intercept, we call that k times beta. Each one has its own coefficient, but they share the same kernel matrix. And then this A is the time per basis function of the Patlak plot, and P is the projection matrix of the PAT system. So we put this linear model. Okay, again, that's a linear model, so we can use an nested EM to perform the reconstruction of the Patlak parameters. So we did this for the total body pads. So here we have the indirect reconstruction, kernel, regularized indirect reconstruction, and then this is a OSEM direct reconstruction for the Patlak slope image, and we also have the intercept image. So details can be found in this paper. Of course, we can, as I mentioned, we can also introduce additional attributes. So for example, the co-register MR image, especially in the brain study. So then we can combine the MR and dynamic pad information together. Okay, here, because the potential mismatch between the MR and the pad, we also introduce a similarity calculation to generate a weighting factor between the 2 kernel matrices. And here's the comparison between different regularized direct reconstruction. So all the reconstruction are direct estimation. So the first one is the nested OT nested EM, followed by a post filter. Okay, the second one is using the MR kernel by itself, a direct reconstruction. The third one using the PAT kernel by itself, and this one is using the PAT and the MR kernel and equally weighted, and the last one is using the structure similarity weighted PAT MR kernel. Okay. Here we have a normal FDG scan with artificially inserted lesion. So the lesion was not present in the MR image. So it's a spherical, but not available in the MR image, just to show the effect of the MR, so potential bias introduced by the MR, and how that can be addressed by the similarity weighting factor. Okay, so as you can see, this is a EM, so it's roughly a spherical shape. If you use the MR information, it's become not spherical because it follows a gray matter structure. So the pad is good, and the structure similarity weighted kernel is also preserved the shape. And we can plot the uptake ratio of the lesion as a function of the standard deviation of the background. So each point is generated by different iterations. So you can see that OT, this is the direct EM reconstruction followed by filter, and that is the MR kernel. Okay, so reduce the noise. But the contrast suffers a little bit. And then with the PAT kernel, and we can further improve the contrast. Okay, in particular, if we compare between the MR kernel and the structure similarity weighted kernel, so they have the same noise reduction, but higher contrast for the lesion. And we can also apply this to nonlinear model as well. So in the Patlak model, we have the KB equals to K alpha, K beta. So similarly, we can have the nonlinear parameters theta. So K1, K2, K3, K4, and FV is equal to this K times alpha, just write it in a simplified form. The problem here is because of this nonlinear relationship between the theta and the x, then this cannot be embedded into this nested EM algorithm anymore. So we actually use a constraint optimization based on ADMM algorithm. Okay. And here's the simulation study of the nonlinear compartment parameters. So again, so we are still showing the KI image, even though this was estimated using nonlinear compartment model. Okay, so we simulate the ground truth image, KI image, and then MR prior image. Then this is the indirect reconstruction, the OTEM reconstruction, no regularization. This is OTM plus local mean filter, and the last one is a kernel regularized reconstruction. And we can also show the contrast of this lesion in artificial lesion as a function of the standard deviation of the wet matter. So we can see the OTEM is here. So this is the indirect reconstruction. OTEM is here, better contrast, lower noise. And then with the kernel regularization is further improve the contrast without increasing the noise. Okay, so the last topic is on the neural network-based regularization. So here I just want to focus on one work. It's a deep image prior, where we use a network structure to regularize the image X. So we have the image is equal to the output of a neural network, and the neural network has an input is the MR image, and then what we're going to change is the network parameter during the reconstruction. And the algorithm, you also use ADMM algorithm, so it has 3 steps. The first one is the penalized maximum likelihood reconstruction with a quadratic penalty. So that's a Poisson likelihood function, and then this is a quadratic penalty with the current neural network output plus the Lagrange multiplier as the offset. And the second step is the network training. So using a single image, one label, that is basically the new image obtained here, plus the Lagrange multiplier. And the last step is a Lagrange multiplier update. Right. So we can put this framework into the kernel-based direct parametric reconstruction just by inserting 2 layers into this neural network. One is the kernel layer over here, right before the output of the network. So essentially, it's a fixed layer, not learned, but it's just use a calculated kernel metrics. And then the output here would be the parametric images, right? And in order to fit into the reconstruction, we need the activity image. And so then we just insert another layer, so connected modeling layer here, that to transform the connected parameters into the dynamic PET images. Essentially, this is just multiplying by the temporal basis function. It's non-trained, not trained. This one is not trained. All the others are trained during the reconstruction. Okay. Also, I have shown a lot of a Patlak model. So here I just show a different linear model. It's a relative equilibrium Logan model. So Kwong apply this methods to carbon-11 Pittsburgh compound B, a scan of MCI subjects. So there's 4 subjects, and so 4 rows. And that's the first column is the MR image for each subject, just for reference. And then the second column is OTEM, direct reconstruction, followed by post-filtering. The next column is using the kernel, MR-based kernel for regularization. And the last column is using the deep image prior for regularization. Yeah. And you can appreciate the regularized reconstruction has lower noise. And then we can also, to look at the differences, to quantify the signal to noise ratio for in different brain regions. So in the paper, there's multiple regions. I just pick one here. And you can see for the unregularized, followed by post filter, even though this direct reconstruction, the CNR is low, and with the kernel MR, it's got better. And then with the deep image prior, it got even higher. Okay, this is true for across all 4 subjects. And there's more result you can find in the reference paper. Okay. And I should also mention, there are other ways you can use a deep neural network, obviously. For example, the 2 in Xie et al., this paper, they use a deep neural network to predict the direct reconstructed image from the indirect reconstructed image. Right? Okay, so in some way, this is equivalent to a denoising network, but also with some bias correction as well, because there's a noise introduced bias in the indirect reconstruction. So it's just not only noisy, but also biased. And also there, Zachary et al. Use a deep neural network actually to predict the parametric image from the dynamic sequence. Okay? So you can have different input, but the end goal can be the same. So those are the different approaches, but and many other examples I won't touch upon because those are not try to optimize objective function. Okay? As I mentioned at the beginning, so there are some unique issues related to the direct reconstruction because we, regardless whether we use a nested algorithm or not, the kinetic fitting and image reconstruction are put into a single loop, right? So they're going to affect each other. In particular, if we have a region that cannot be fit by the predetermined kinetic model, then there will be bias in that region. In the indirect reconstruction, because each pixel fit separately, so there's no propagation of the bias from one pixel to the next. But in the direct reconstruction, we can observe this bias propagation from one region where we have a model mismatch to another region where actually the model is correct because of the reconstruction process. This was studied by Konasetis and Reader. And here it shows, this is the top row is a noise, the matched model. So where you don't see the bias, the image show are the bias. And the bias only occur at the boundaries. That's expected in all the reconstruction. And the bottom is actually, we have the mismatch model in the liver because the liver has dual blood input and we only use one blood input to fit. So then the liver in both direct and indirect, we see a large bias. But in the indirect, the bias is pretty much limited inside the liver region, but in the direct reconstruction, you can see this propagating to some other regions in the field of view. Right? This is for the noise-free data. You can obviously observe this effect. But when you go to noisy data, actually the direct reconstruction still outperform the indirect reconstruction because this bias propagation, even though it's still there, they're being buried by the noise in the indirect reconstruction. So the indirect has much higher noise and generated bias. So therefore, I actually have even higher bias than the direct reconstruction. So nonetheless, so people have developed methods to mitigate this bias propagation. So one example is use the adaptive kinetic modeling. So with a secondary basis function, or to use a clustering methods to identify the region of model mismatch. And another work is to use a probabilistic a graphic model to model the uncertainty in the model, kinetic model at every point. So that can mitigate this bias propagation issue as well. Okay, so I think, so in summary, I hope I have convinced you that direct reconstruction of kinetic parameters from raw PET data can reduce noise in parametric imaging. And various computationally efficient algorithms have been developed in the past 2 decades that enable adoption of direct reconstruction in real applications. And the combination of direct reconstruction with machine learning show promises in further improve the image quality. Okay. And I just want to thank so many people who have contributed to this work, in particular the past and current lab members, collaborator at UC Davis, MGH, Canon, and UIH. So thank you for your attention.